In this video, we're going to do a bunch of AP Chemistry multiple choice questions to see what they're like and to see some strategies for solving them. If you want, you can download questions first and try them yourself. Just check out the link in the description. This video is going to be helpful at pretty much any time during your AP Chem journey. The questions only cover the following topics, which you probably already know from a pre-AP Chem class. So, you can try these questions even if you haven't started AP Chem yet. But all these topics show up on the real AP Chem test, so the video will still be super helpful at any time before the exam. Now, here's some important background. Students often feel that the multiple choice questions, or the MCQs, are the hardest part of the test. When they try the MCQs, there are a couple really common things students say. My teacher never taught me this. I didn't know I should memorize this, and I never learned any of this. So common for people to say these things when they first check out the MCQs. But this is a totally normal way to react. And if this is your reaction, it doesn't mean that you can't do super well on the test. But you have to learn to move beyond these worries, shift your mindset, and tackle the problems in a different way. That's what we're going to talk about in this video. Now, MCQs on the AP Chem test are different from those you've seen in pretty much most other tests. Typical MCQs usually test one thing that you already know, and they're honestly pretty easy. Okay, like this one. Which of the following elements is a metal? Carbon, oxygen, silicon, or zinc? Seriously, right? This is the type of MCQ I bet you're used to. And you're usually psyched when you have a multiple choice test because it's probably going to be crazy easy. But not on the AP Chem test. The MCQs are totally different. To solve just one MCQ, you'll probably need the information you already know from one topic, combined with information you already know from at least one other topic. Then, you usually also have to apply some reasoning and kind of puzzle solving, add in some math, and only then can you get to the right answer. So an AP Chem MCQ is testing all of these things at once. So we are going to look at some AP style MCQs so you can get the hang of what's expected. You can see how you solve them, and we'll point out tricks and strategies along the way. Again, you can download the problems if you want, the link in the description. Let's go ahead and start. The formula for sodium arsenate is Na3ASO4. What is the formula for calcium arsenate? Now, you might think right away, wait. I've never seen arsenate before. My teacher never told me to memorize it. I guess I can't answer this question. Wait. But pretty much no one has arsenate memorized. I don't. That's the point. You need to approach this problem like puzzle solving. The question isn't, have you memorized arsenate, or did your teacher tell you to memorize arsenate? The question is, can you figure this out based on what you already know? Here's how we do it. The question gives us the formula for sodium arsenate. Then it asks us to predict the chemical formula for calcium arsenate. Okay, so to do this, we have to figure out the charge on the arsenate polyatomic ion. We'll start by breaking this formula down into the ions that make it up. There are 3 sodium ions, and you should definitely know that sodium always forms a 1+ charge, meaning that in total we have a +3 charge, adding these 3 positive ions up. Now, this +3 charge needs to be balanced out by the anion, or by the negative ion, okay? There's only one arsenate ion, so it must have a -3 charge. So it's ASO4 3-. Now that we've figured that out, we have to determine the formula for calcium arsenate. This brings us to the next part of the question. Calcium always forms +2 ions, and we just established that arsenate is 3-. So we need to balance this 2+ with this 3 minus. That means we'll need 3 calcium ions, which makes an overall +6 charge. And this is balanced by 2 arsenate anions, which makes an overall -6 charge. So +6 cancels -6, and we have a neutral compound. Our correct formula is Ca3 parentheses AsO42. Remember these parentheses because arsenate is a polyatomic ion. And that's choice D. Now, we could go over these other answer choices and talk about why they're wrong, but on questions like this, it usually just makes sense to find the correct answer and go with it. Okay, so now that we've talked through this, you might see why I wanted to start the video with this question. Because many times on the AP Chem MCQs, you'll see a question and your initial response will be, I've never seen this before. You know, my teacher didn't tell me to memorize this. I am done. It's natural to think that there's no way you can possibly answer it. You don't know the background information. But to succeed on the test, you gotta shift your perspective and think, this is probably supposed to be unfamiliar. I'm probably not supposed to already know it. How can I figure it out? And that's what we're going to be focusing on throughout AP Chem. How can I figure it out? Okay, our next question. A 64-gram sample of an unknown gas occupies 44.8 liters at STP. Which of the following could be the identity of the gas? Okay, so we got some numbers here. This is a math-based question, but it's probably a little bit different from the ones that you're used to doing. Most students, by the time they get to AP Chem, are really good at stringing together conversion factors like this, canceling the units to solve math problems. But this problem is tricky because you can't solve it very easily by just stringing together some conversion factors. Instead, you need to understand what these conversion factors really mean, and then you'll use that information to create sort of more of a step-by-step logical method of solving. Here's how we're going to attack it. Notice right off the bat that we're talking about STP here, or standard temperature and pressure. At STP, there's a very important relationship that you should have memorized. And that's that 1 mole of gas takes up 22.4 liters. And we can express that as 22.4 liters per 1 mole. This is a really important relationship to have memorized. So, we can use this to figure out how many moles of gas we have. Okay, we have 44.8 liters of our unknown mystery gas. How many moles is that? Well, since 1 mole takes up 22.4 liters, we can divide that by 22.4 or multiply by this conversion factor, and we get 2 moles of gas. Now, even though you can use a calculator on these problems, you'll see that the math is usually pretty straightforward. You'll often see relationships like halves, doubles, and triples that make calculation really easy. So we have 2 moles of this gas. Next, we need to figure out the molar mass of the unknown gas. In other words, how much does 1 mole weigh? Well, the total sample is 64 grams, and we know now from the first calculation that we have 2 moles of it. So we'll just divide 64 grams by 2 moles, which gives us 32 grams per mole. That is the molar mass now of our unknown gas. Now, we have to figure out which of these answer choices has a molar mass of 32 grams per mole. To do this, we'll need the periodic table. Luckily, you have one for the test. Okay, so first off, oxygen. According to the periodic table, it's got a molar mass of 16 grams per mole. But remember, this is O2, diatomic oxygen. There are 2 moles of oxygen per molecule of O2, so the molar mass is 16 plus 16, giving us 32 grams per mole. And that's the molar mass we're looking for. A is probably right, but let's double check the others just to be sure. Next is argon. Argon has a molar mass of 39.95 grams per mole, so it doesn't match the correct molar mass. We can cross that out. Sulfur trioxide, 1 sulfur, 3 oxygen. Whoa, 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 way too big. Nowhere near close. We can get rid of that. And finally, carbon monoxide, CO, carbon plus oxygen, and that is too low, so we can get rid of that as well. And there you have it. Choice A is definitely correct. Now, for this question, you can see that the math wasn't hard at all. Basically, just dividing by, dividing this by this to get 2, dividing this by this, dividing by 2. You can do it without a calculator, right? But there's not a simple equation that you can use. There's not a simple string of conversion factors that you can put together. So you have to think through each step using information you already know about moles, about STP, stuff like that, and put it together in a logical way. All right, here we have some particle diagrams. AP Chem Test loves to use these, okay? An aqueous solution of 1 molar potassium nitrate has a boiling point of approximately 101 degrees Celsius. Which of the following diagrams most accurately represents the system at a time shortly after it has reached 101 degrees Celsius? The AP Chem Test likes to use these particle diagrams to see if you understand how molecules and atoms might rearrange during certain physical and chemical processes. So let's take this one step at a time. There are a couple different processes going on here. First of all, we have this aqueous solution of potassium nitrate. How should that be depicted? Well, KNO3 is a very soluble salt. So when it dissolves in water, it will fully dissociate into K plus and NO3 1-. The key here is that NO3 1-, the nitrate polyatomic ion, stays together in water. All of these atoms are bonded as a unit. So in A, B, and C, you'll see that nitrate here is correctly depicted as being made up of these atoms all connected together. And they're also surrounded by or solvated by water molecules in the correct orientation. But over in D, the atoms that make up nitrate, the nitrogen and the 3 oxygens, they come apart. They're just floating around here. And that's incorrect. So we can cross off D. Okay, 1 down. Next, there's a phase change happening here, and that's the water boiling. The temperature is at the boiling point, so liquid water is turning into gaseous water. Now, if you're wondering why the boiling point here is 101 degrees and not 100 degrees, well, it's because of the dissolved solute, the potassium nitrate here, and that slightly raises the boiling point, just slightly. That's why it's 101 instead of 100. Okay, but anyway, the point here is that water remains together as H2O when it's in the gaseous form. And we can assume that gases are located in this space above the containers. So here we have the proper depiction of water as H2O in the gaseous state. But over here, you can see that the atoms have come apart. This is a really common misconception, even amongst AP Chem students. In gas form, molecules stay together. The component atoms don't come apart. Now, over here in C, the water is also correctly depicted. So we can get rid of B because of this, but we'll keep A and C for now. All right, now finally, we need to ask, what are the compounds that are turning into gas here? The problem gives us the boiling point of the mixture, 101 degrees Celsius. But the important thing to keep in mind here is at 101 degrees Celsius, only the water, only the H2O vaporizes. KNO3, potassium nitrate, is an ionic salt. It doesn't boil anywhere close to 100 degrees Celsius. It only vaporizes at around 400 degrees. But here in C, we see potassium and nitrate in the gaseous state. So that is definitely wrong. We're not going to be getting any gaseous potassium nitrate at 100 degrees Celsius. So we can get rid of that. And on the other hand, A here shows only water in the gaseous state. So A is our answer. It correctly depicts all 3 of these processes. So what's the takeaway here? It's that particle diagrams are something to watch out for and to be familiar with for the AP Chem, particularly for the MCQs. It's one thing to be able to write equations like this or to understand them when you see them in a textbook, but it's another thing to understand how the atoms and molecules would correctly be drawn or depicted in these different situations. So as you go through AP Chem, always ask yourself, when you're learning about a process, always ask yourself, what would the molecular view look like here? If you can answer that question, if you know how the atoms and molecules would be correctly depicted, particle diagrams will essentially be free points. All right. This is a great AP style question because it's asking multiple things at once and asking you to use the information you already know to solve new problems. The following table shows the first 5 ionization energies, or IE, for a neutral element measured in kilojoules per mole. Which of the following could be the full electron configuration of that element? Now, when I say that this is a great AP Chem style question, here's what I mean. A more basic question for a pre-AP class might look something like this. What's the electron configuration for nitrogen? And you have 3 that are obviously wrong and 1 is correct. All right? But for the most part, the AP exam already assumes that you know how to do this. So you're very unlikely to get such a straightforward question. Instead, you've got to use this knowledge, but just as background, as fundamentals to solve a new problem that's more complex. Getting back to this, where do we start? Well, here we have some information about ionization energies. And as a review, ionization energy is the amount of energy needed to remove an electron from an atom. These numbers are the electrons in order. So this is the amount of energy to remove the first electron from the atom, and then second, third, fourth, fifth, and so on. When we're looking at a series of ionization energies like this, we want to look to see if there's a big jump in the values anywhere. That jump can give us very important information. And you can see a big jump right here from 1451 to 7732. Big jump. These are close in value and these are close in value. Now, that big jump tells us that, in a sense, these electrons with relatively low ionization energy are very easy to remove, whereas these with relatively higher ionization energies are hard to remove. Why is that? What change happens between these two and the rest here? Well, electrons are particularly hard to remove if they're part of a stable noble gas configuration. Sometimes we say that means that they're part of a filled core level. Since these two electrons are easy to remove, that means that for this atom, we're able to remove 2 electrons before we arrive at a stable noble gas configuration, which means that this atom has 2 more electrons above a stable noble gas configuration. So, if this atom has 2 more electrons than a stable noble gas configuration, well, what does that stable configuration look like? Here I've got the configurations of some noble gases, and with the exception of helium, you'll notice that all of them have their S and P subshells completely full. S2P6, S2P6, S2P6. So now let's evaluate these choices. D. There are 4 electrons between the 3s and the 3p. That doesn't work. Now, if we had just 2 here, if we had just the 3s2, then we could lose these 2 and we'd be left with a full sp. But we don't. We have 4 here instead. So we don't have 2 more, we have 4 more. And to fully fill the s and p, we need 4 more electrons. And then we need 2 extra after that. So there's no way that this is correct. Okay, for choice C, we do not have a full S and P. we have 6 electrons, so we need 2 more to completely fill this. And then remember, our mystery atom has 2 more than the totally filled shell there. So we need 4 more electrons. This is a common mistake. Sometimes people see these 2 that are easy to remove, that are the 2 more than the stable noble gas configuration, and they think, well, that means that you need 2 more to get to the noble gas configuration. So some students will pick this because they'll say, we need 2 more to get to S2P6. This tells us that there are 2 more and they'll choose this. Nope, it's wrong. This is 2 more above the noble gas configuration. Okay, so now we have A and B, which are both decent choices. Deciding between these 2 can be a little bit confusing. They both have 2 electrons in the 4s, which in both cases seems like 2 easy electrons to lose. But the question here is, what remains when you lose these 2 electrons? This choice A is really tempting to many students because we see a completely filled n equals 3 shell. The s, p, and d orbitals are all filled. But it's not the full level that gives noble gas stability. It's the full s and p orbitals. Argon is stable without the filled 3d orbitals. And krypton is stable without the filled 4d and 4f orbitals. It's about the s and the p. So losing these 2 electrons won't leave us with a full s and p. We'll get the d as well, so we won't see this big change in ionization energies. On the other hand, B is the correct answer. We have these 2, we lose these 2, we lose the 4s2, and we have a full S2P6 right here. And this, once we lose the 4s, also happens to match the electron configuration of argon, which is exceptionally stable. Now, in the AP Chem MCQs, there's often more than one way to correctly solve a problem. And here's another way that you could do it. This big jump in ionization energies means that the atom will most easily or readily lose 2 electrons. And that means that it will most readily form a 2+ ion. Well, the elements in group 2A here all readily lose 2 electrons. This group is in the S block of the periodic table, and all of the elements in this column have electron configurations ending in S2, and the lower d orbital has not started to fill yet. Atom B would be here, but atom A would be here as that d subshell starts to fill. Now, if you can look at a periodic table and determine an element's electron configuration by its location, that's a really useful skill that will be tremendously helpful. And if you don't know how to do it already, you'll need to learn that during AP Chem. It will be really, really helpful for the exam. Anyway, like a lot of AP Chem multiple choice questions, this one is tricky because you have to put together different pieces of information. You have to understand ionization energy, interpret the table, and then figure out how that relates to electron configurations, or how that relates to the location of elements on the periodic table and thus their electron configurations. Okay, in a solution of K3PO4, the concentration of K+ is 1.5 molar. To create the solution, how many moles of K3PO4 would be dissolved in 0.50 liters of solution? This is actually a pretty straightforward question, but it can trip people up because it combines 2 different concepts. Let's start with a molarity of K+. We'll eventually need to know moles of K3PO4, but to get to that, we need to understand what happens when this dissolves. Potassium phosphate is very soluble, so when it dissolves, it will fully dissociate. 1 unit of potassium phosphate will yield 3 units of K+ and 1 unit of PO43-. So there's a 1 to 3 ratio here. We're given the molarity of the potassium ion, which is 1.5 molar. So we can use this ratio to figure out what the starting molarity of potassium phosphate would be. It would be 1/3 of this, or 0.5, 1 to 3. So that's the first part of our problem. Now that we have the molarity of potassium phosphate, we can do some math to figure out the moles. We got molarity equals moles over liters. We are given the molarity, or we figured out the molarity from this piece of information. So now we can set moles as our variable. Liters, we know, 0.50 liters. Now we want to solve for x, so we're going to rearrange this. X equals molarity times liters. We can rewrite molarity as moles over liters. That also pulls the liters out and allows us to see that it's on the bottom here. It's on the top there, so we can cancel it, and we can feel confident that we've set this up correctly. It also is nice and neat to be able to cancel the liters. And the multiplication this times this, pretty simple, gives us 0.25 moles. And that matches choice D. Which of the following is the correct mass spectrum for magnesium? Now, literally, some people will see a question like this and say, oh no, I should have memorized the mass spectrum for magnesium. No, you shouldn't have. You got to figure it out, and you probably already know everything you need to solve this. So what are these graphs showing? On the x-axis, we have 3 isotopes with different masses, 24, 25, 26 AMU. And on the y-axis, the percent abundance of each. There are few key pieces of information that we need to put together to answer this question. First, the atomic mass of magnesium, we can get that from the periodic table, 24.30. And we also need to remember that the atomic mass of an element is a weighted average of the different isotope masses. Then we just have to interpret the graphs. Let's do a close-up look at D. You've probably learned that the equation for calculating atomic mass from isotope abundance looks like this. You multiply each isotope mass by the percent abundance expressed as a decimal. So we have 24 times 0.4 plus 25 times 0.3 plus 26 times 0.3, which gives 24.9, which is definitely not magnesium's real atomic mass. So this is not the right graph. And since you can use a calculator on the MCQs these days, this would be an okay way to do it. But there's actually a faster way. As with a lot of the stuff on the AP Chem exam, you can really just eyeball it. If you're going to look at these graphs and eyeball it, or kind of think it through, the reasoning might sound like this. These abundances are almost the same. If they were totally the same, the average would be 25. But since 24 is a little higher, the average will be pulled down a little bit to just under 25. Maybe 24.9 or 24.8, but not 24.3. And as you can see, that reasoning syncs pretty well with the actual calculation. So we still know this is definitely the wrong answer. Now we'll move on to C. What would the reasoning look like if we didn't want to do the math and we just wanted to eyeball it and think it through? We might say 25 is greatest. If bars on either side were the same height, the average would be exactly 25. Since 26 is higher than 24, the average will be a little above 25. Definitely wrong. And if we were to do the math, we see that that confirms our reasoning, and we know that C is wrong. On to B. 24 and 26 are almost equal. That would put the average about 25. 26 is a little less than 25, but there's also a small bit of 25. So the average is still probably very close to 25, not anywhere near 24.3, And there's the math that backs up our reasoning. B is also incorrect. Finally, A. We're pretty sure this is going to be correct, but here's the reasoning. 24 is the most abundant by far. 25 and 26 only contribute a small amount. The average will be closest to 24. And there you go. Do the actual math, and you get 24.3, which matches the actual atomic mass of magnesium. So this was a good example of a problem that's kind of like a puzzle. Now, you weren't supposed to memorize the mass spectrum for magnesium. You put the puzzle pieces together. And there's another good tip here. Even though you can use a calculator on the AP Chem test these days, you shouldn't ever be drowning in math during the MCQs. You've only got about 90 seconds per question to answer. So if you're in a situation where you're just slogging through calculations, there's probably a better, simpler way to just think it through, just like we did here. A chemical reaction is represented by the unbalanced equation above. The diagram beside it shows relative amounts of starting reactants. Which diagram correctly shows the relative amounts of substances after the reaction has reached completion? You've probably never seen a question like this in a chemistry textbook, but this one is testing a lot. It's asking if you really understand what's happening during a chemical reaction, how reactants combine, what it means to balance an equation, and how limiting reactants work. All of that is tested here. So here's a reaction that we're working with. First off, let's balance it. There we go. Sometimes the AP test will casually mention that an equation is unbalanced. That's usually an intense warning sign, and the equation needs to be balanced in order for you to correctly answer the question. Now, this box here shows the reactants at the start of the reaction. Let's draw what they would look like after the reaction completes. So, first, 1A2 is going to combine with 2 B2s, and that will create 2 AB2s, just like in the balanced equation. All right. Now, these are all used up. Let's run the reaction again, and we can't. We don't have enough B. We need 2 B2, but we only have 1. That means that B is a limiting reagent, or limiting reactant. We have plenty of A, but without more B, we can't continue. So these are the only products that we can make. Now, the unused starting reactants will also be present at the end of the reaction, so we'll move these over here, and the final reaction mixture is going to look like this. And that matches choice B. Now, this question can be pretty tricky for a lot of students, so we'll take a minute and go through some of the other choices and discuss why they're wrong. So right away, it's probably clear why C is wrong. C has the correct amount of products. But remember, the unused reactants don't just disappear. They're still present at the end of the reaction. So they're here mixed in with the products. That's why C is wrong. Now, how about D? Well, D shows the reaction continuing, but in a way that doesn't follow the equation. Here, 1A2 combines with 1B2, which means that the A2 splits, giving us a single A. But that's not how the reaction works. It doesn't fit with the equation. We can't just end up having 1A by itself. The reaction can only happen if we can make AB2 and only AB2. Notice there isn't a single isolated A on this side of the equation. So D is not correct. And it also shows the unreacted A. If you're confused about where these two come from, these are just the unreacted A that would have moved over here into the products. That's where that comes from. But nonetheless, D is definitely wrong. And finally, what's going on with A? Well, A happens according to the unbalanced equation, okay? We have 3A2, 1, 2, 3, and we have 3B2. We combine these with these from the unbalanced equation. It looks like it's a 1-to-1 ratio, and we would make, according to the unbalanced equation, 3AB2. And then we'd have one of these left over, and there it is. So A proceeds according to the unbalanced equation. Totally wrong. Get rid of it. Also, A doesn't follow the conservation of matter. In other words, atoms are disappearing or getting created, and that can normally happen. And in fact, we can tell that 2 of these answer choices are wrong right away because the number of atoms is not conserved. We started with 8A atoms and 6B atoms. We need to have the same number at the end of the reaction. But atoms disappear in both A and C. That's another way to know that these 2 choices were wrong. So, as you can see, a question like this might look very simple, but to get it right, you really need to understand how reactions work. You can't just do calculations with a bunch of conversion factors to solve a problem like this. You really have to think it through, understand how reactants combine to create products. All right, here is a question that deals with lab procedure and lab calculations. A student performs an experiment to determine the molar mass of an unknown monoprotic acid. A certain mass of acid is dissolved in distilled water and titrated with 1.0 molar of sodium hydroxide. All of the following errors result in the calculation of molar mass being too low, except for which one? So, to answer this question, let's figure out what steps the student would take and figure out the calculations that would happen at each of those steps to then figure out how errors could creep in and how they'd affect the final result. So, first, the student would weigh out a certain amount of acid and would dissolve it in a certain volume of water. Next, they would titrate this acid with the 1.0 molar sodium hydroxide. They'd record the volume of sodium hydroxide used to get to the endpoint. The volume of sodium hydroxide is what's needed to completely neutralize the unknown acid. And since you know what the molarity is, you can multiply that times the volume in liters to get the number of moles of sodium hydroxide. Once the moles of sodium hydroxide have been determined, that tells us the number of moles of acid. Because the problem told us that it's a monoprotic acid, we know it's a 1-to-1 stoichiometric relationship at the endpoint, so moles of sodium hydroxide equals moles of acid. And finally, the student would divide the mass of the acid by the moles of the acid, grams divided by moles, to get the molar mass of the acid. So as you can see, there's several places where error can creep into these calculations. Okay, let's get rid of the question so we can make some more room. Move this on up. Okay, great. Now let's look at each answer choice. Just remember, we're looking for the one that gives us a higher molar mass than we should have. In choice A, the student forgot to convert milliliters to liters and used milliliters in the molarity calculations. If that happened, you can see that the number of moles would be much bigger because moles equals molarity times liters. If we used milliliters instead of liters, if we forgot to convert, this would be a much larger value here, bigger by a factor of 1,000. We'd calculate way too many moles of sodium hydroxide, meaning that we'd get way too many moles of acid, and this value, moles in the denominator, would be way too big, so we'd divide this by a very large number, giving us a smaller molar mass than we should get. So A is not correct. Next, there's B. The burette was rinsed with distilled water and not 1.0 molar sodium hydroxide solution. Okay. If the burette was washed with distilled water, the sodium hydroxide would be slightly diluted. So that means that the actual concentration of sodium hydroxide would be lower than 1 molar, but you wouldn't know that. And that means that you'd need more volume, a larger amount of liters to reach the endpoint. So you'd have a larger value of liters or volume than you should. This would mean that you would calculate too many moles because this is too big. That would then give us too many moles of acid. And once again, the denominator would be too big. Dividing this by a number that's larger than it should be will give us a smaller molar mass. So B is also wrong. Choice C says that the student overshot the endpoint by adding too much 1.0 molar sodium hydroxide solution. If the student added too much sodium hydroxide, once again, we'd see a larger volume for larger value for liters than we should have, which gives us too many moles of sodium hydroxide, too many moles of acid, and once again, a larger than expected volume value in the denominator. Since it's our last option, choice D is probably going to be our answer, but let's check it to be sure. Choice D says that after weighing the solid acid, some is lost before dissolving. If this occurs, the mass of the acid is actually lower than what was recorded. We think it's more, but we lost some, so actually we have less. That means that because there's less acid there, it's going to take less sodium hydroxide to neutralize it. The value for liters, for the volume, is going to be smaller. That means that the moles of sodium hydroxide is lower, translating to too few moles of acid. That means that we're dividing this by a smaller number than we should be, which means that the molar mass is going to be larger than it should be. That means that D is correct. This is the only option where the mistake gives us a molar mass that is too high instead of too low. When you do problems like this, you need to understand the lab procedure itself, and then you also need to think about how an error in one measurement or calculation will affect the other ones later on. Definitely not an easy question. You've got to attack it step by step, thinking about the consequences of each step. Okay, here's our last question, and it really flexes the MCQ muscles. It's like perfect kind of question they want to ask to trick you. All right, a 50-gram sample of aluminum is at 100 degrees Celsius. It's placed in 50 grams of water at 20 degrees Celsius. The specific heat of aluminum is 0.89 joules per grams times degrees Celsius, and the specific heat of water is 4.18 joules per grams times degrees Celsius. The system is allowed to reach thermal equilibrium. Which of the following is a true statement? Now, when you read this question, you might think, this is going to require some intense calculation. And in fact, a full mathematical answer might look something like this. Whoa, whoa, whoa. But who has time for that on the MCQs? Remember, you've only got 90 seconds to answer each one. So if you're ever in a situation on the MCQs where you're doing a ton of math, there's usually a simpler, more straightforward way to solve it by thinking it through. That's certainly true here, and let's look at that approach. The question is about specific heat, temperature, and heat transfer. If we're talking specific heat, what's the big picture here? Well, specific heat tells us how much heat energy is needed to raise 1 gram of a substance by 1 degree Celsius. Now, the problem tells us that we have 50 grams of aluminum and 50 grams of water. They have the same mass, so we don't really have to worry about mass for this problem, which is nice. One fewer thing to worry about. But the substances have different specific heats. Aluminum has a specific heat that is relatively low. And water has one that is pretty high. That's the key thing. They're different specific heat values. See, if these substances absorb the same amount of heat energy, the little Q here, the temperature of the aluminum will go up a lot, but the temperature of the water will only go up a little. They'll have very different changes in temperature. That's a delta T here. Because of its high specific heat, you can think of water as being more resistant to temperature change. How is this relevant to the problem? Well, it says that we put 50 grams of aluminum in 50 grams of water. The aluminum will lose heat energy and give it to the water. So the aluminum will cool down as it loses heat energy, and the water will heat up as it gains the heat energy lost by the aluminum. And this transfer of heat energy will stop when the aluminum and the water reach the same temperature, also known as thermal equilibrium. An important point here is that the heat lost by the aluminum is the same amount that is gained by the water. So, what will that final temperature be? What will the temperature be when the heat transfer stops? Well, that's where specific heat comes in. Let's look at the answer choices. Choice A says that the final temperature will be 60 degrees. This value is halfway between the starting temperatures. It's the average. This plus this divided by 2 equals 60 degrees. But this average right in between the two starting temperatures assumes that both substances experience the exact same temperature change. But they don't. Remember what we said earlier. Aluminum has a lower specific heat than water, so its temperature will change much more than water. So if the heat lost by the aluminum is equal to the heat gained by the water will only change its temperature a little bit compared to the aluminum. Remember, this low specific heat means water is very resistant to temperature change. Now, this average temperature of 60 degrees would represent an equal change in temperature. They both would have to change the same amount, so it can't be right. Cross it off. Choice B is easy to eliminate. It's a gimme. It describes the exact opposite of what happened. Heat was lost by the aluminum and gained by the water. So that's wrong. C says the aluminum has a higher change in temperature than the water. Now we're talking. Let's look at our delta T arrows again, right? The temperature of the water will change less than the temperature of the aluminum. Again, the same amount of heat is transferred, lost by the aluminum, gained by the water, but they respond to it differently. The water temperature goes up a small amount, but the aluminum goes way down. So choice C is probably correct, but let's look at choice D anyway. The heat gained by the water is approximately 4 times the heat lost by the aluminum. See what they're doing here? They're trying to trick you. Water does have a specific heat value that is about 4 times larger than aluminum, but the heat lost by the aluminum is equal to the heat gained by the water. They gain and lose the same amount. Don't get confused by the difference between specific heat, temperature, and heat energy gained and lost. So D is incorrect, and choice C is the one to go with there. Just as we've said earlier, the key point with this question is that if you find yourself drowning in math on an MCQ, working through tons of calculations and equations, there's probably a simpler and easier way to solve the problem if you step back and think about the fundamental concepts that are involved. Okay, so if you've made it all the way through these problems, you've learned a ton about the multiple choice questions on the AP Chem test. We've talked a lot about how these problems are designed, why they can seem really tricky, and how you can use some strategies to attack them. And I think we can summarize all the stuff with a few key points. First off, the material may seem unfamiliar, but you probably weren't supposed to already know it or have it memorized. Usually, you need to take what you already know and use it to solve unfamiliar problems. MCQs often cover 2 or more topics at the same time, so be alert for that. The math usually is very easy, but you have to know what you're doing, and you can't just plug numbers into an equation or use strings of conversion factors. The MCQs aren't, for the most part, testing to see that you can use an equation. They're asking, do you understand the math, what you're doing, and why? Many questions, like particle diagrams, ask about concepts at a very fundamental level. Make sure you truly understand the basics. Don't be one of those AP Chem students who can solve really complicated calculations, but thinks that the atoms in water come apart when it turns into a gas. And finally, if you find yourself doing a crazy amount of math, there's almost definitely a simpler way to solve the problem by thinking it through. If you can keep these points in mind, you'll be ahead of so many other students when it comes to tackling the MCQs.